Hello everyone, myself Vidinesh and my roll number 536 and my topic is mastering concurrent computing through sequential thinking. One of the most daunting challenges in information science and technology has always been mastering concurrency. Concurrent program is enormously difficult because it copes with many possible non-deterministic behaviors of tasks being done at the same time. These come from different sources including failures, operating systems, shared memory architectures, and asynchrony. Concurrency was once a specialized discipline for experts, but today the challenge is for the entire information technology community because of two disruptive phenomena: the development of networking communications and the end of the ability to increase process speed at the exponential rate. Increases in performance come through a concurrency as in multi-core architectures. First, a sequential specification of an object or service that can be accessed concurrently states the desired behavior only in executions where the processes access the object one after the other sequentially. The second part of the strategy is to provide implementation techniques for efficient, scalable, and fault-tolerant concurrent objects. Locks enforce exclusive accesses to shared data and concurrency control protocols. The bridge establishes a connection between the executions of a concurrent program and sequential specification. It enforces safety properties by which concurrent executions appears as if the operations invoked on the object were executed instantaneously in some sequential interleaving. Mutual exclusion. Concurrent computing began in 1961 with what was called multiprogramming in the Atlas computer, where concurrency was simultaneous when telling stories where things happen concurrently interlacing the execution of sequential programs. Concurrency was born in order to make efficient use of a sequential computer, which can execute only one instruction at a time, giving users the illusion that their programs are all running simultaneously through the operating system. As soon as the programs being run concurrently begin to interact with each other, it is realized how difficult it is to think concurrently. A mutual exclusion program consists of the code for two operations, acquire and release, that a process invokes to bracket a section of code called a critical section. The usual environment in which it is executed is asynchronous, where process speeds are arbitrarily independent from each other. A exclusion algorithm guarantees two properties. Mutual exclusion. No two processes are simultaneously execute in the critical section. Deadlock freedom. If one or several processes invoke acquire operation that are executed concurrently, eventually one of them terminates its invocation and consequently executes its section. Deadlock freedom does not provide specific timing scenarios from occurring in which some process can never enter the critical section. The stronger starvation freedom progress condition states that any process that invokes acquire will terminate its invocation and will consequently execute its critical section. Mutual exclusion was the first mechanism for mastering concurrent programming through sequential thinking and led to the identification of notions that began to give a scientific foundation to the approach, such as the concepts of progress condition atomicity. It is the origin of the important area of the concurrency control by controlling access to data using locks. At the beginning, a critical section was encapsulating the use of physical resource, which by its own nature is sequentially specified. A shared object is different from a physical object in that it does not a prior require exclusive access. A process can read the data of a file while another process concurrently modifies it. The lock-free approach makes possible to envisage implementations of purely digital objects without using mutual exclusion in a way that operations can overlap in time. In a shared memory context, there are implementations from very simple registers that only one process can write and another can read, all the way to a multi-writer, multi-reader MWMR register that every process can write and every process can read. Distributed message passing systems often support a shared memory abstraction and have a wide acceptance in both research and commercial computing because this abstraction provides a more natural transition from processes and simplifies programming tasks. An algorithm that implements an atomic read-or-write register on top of system of n asynchronous message passing process where at most t less than n by 2 of them may crash. A proof of impossibility of building an atomic register when t n by 2. This section presents the algorithm referred to as the ABD algorithm, which illustrates the importance of the ideas of reducing concurrent thinking to sequential reasoning. Design principles of ABD. Each return value has identity. Each process is both a client and a server. Design principles of ABD. Intersecting quorums is process PA broadcasts a query to all the processes and waits for acknowledgements from a majority of them. Such a majority quorum set has the following properties. As T less than n by 2 waiting for acknowledgements from a majority of processes can never block forever the invoking process. A read or write register is a special case of an object. In general, an object is defined by the set of operations that processes can invoke and by the behavior of the object when these operations are invoked sequentially. These can be represented by an automaton or by a set of sequential traces, consensus, consensus at the core of many situations where sequential reasoning or concurrent programming is used, including state machine replication or agreement problems. Let cons be a consensus object, and a process PA can invoke the operation cons dot propose V once. The invocation eventually returns a value V. The sequential specification for cons is defined by the following properties. Validity. If an invocation returns V, then there is cons dot propose of V. Agreement. No two different values are written. Termination. If a process invokes cons dot propose of V and does not crash, the operation returns a value. A concurrent stack can be implemented by executing the operations pop and push using mutual exclusion. The general idea is for the processes to agree on a sequential order of concurrent invocations, and then each one of this to stimulate the sequential specification automon locally. We illustrate here the approach with a total order broadcast mechanism for reaching a required agreement. Total order broadcast. The TO broadcast abstraction is an important primitive in distributed computing, which ensures that all current processes receive messages in the same order. It is used through two operations, to broadcast and to deliver. A process invokes two broadcasts of M to send message M to all other processes. As a result, processes execute to deliver when they receive a totally ordered message. To, to broadcast illustrates one more general idea within the tier of mastering concurrent programming through sequential thinking. The identification of the communication abstraction that facilitate building concurrent objects defined by a sequential specification. Given that consensus and two broadcasts are equivalent, the state machine replication algorithm represented above cannot be implemented in asynchronous systems where processes can crash. A fundamental result in distributed computing is the impossible to design a deterministic algorithm that solves consensus in the presence of asynchrony, even if only one process may crash either in message passing or read or write shared memory systems. Thus, sequential thinking for concurrent computing has studied properties about the underlying system that enable the approach to go through. There are several ways of considering computationally stronger read or write or message passing models where state machine replication can be implemented. Some ways mainly suited to message passing systems are present in the sidebar circumventing consensus impossibility. Uh, that's it. Thank you, everyone.